In our last session, we built our first MLP. We saw that a simple shallow MLP works fine, but when we try to make it deeper, we run into the vanishing gradient problem, and our model failed to learn. In this video, we're going to build on that knowledge. Our goal is to construct a robust, flexible, advanced MLP. We'll introduce several key techniques used in modern deep learning, such as better weight initialization and normalization to make our deep models train efficiently. We'll treat this as a scientific experiment, also known as an ablation study, to see which components give us the biggest performance boost. Let's start by looking at our initial setup here. And if you notice, there is a new one here, utils, which is a Python file that I created, and it contains all of the helper functions that I'm going to use for plotting, running diagnostics, and visualization of the weights, of the learned weights. This way, I'm trying to keep the main script clean, and we want to focus on the core logic of the model and the experiment. Okay, so next in the data preparation, I added another step that basically normalized the input data to have a mean of 0 and a standard deviation of 1. This simple step makes the training process significantly more stable and often faster. Normalization creates a much smoother optimization landscape, and the optimizer can easily navigate through this well-behaved landscape compared to before. Moreover, it basically ensures all of the input features are on a comparable scale, prevents some weights from needing to learn extremely large or small values. So with that, let's go ahead and write our model class. We are going to call it Advanced MLP. It's, of course, going to inherit all of the goodies in an N module. So this is the init method that I wrote, where I added a few knobs to turn, including the choice of activation, which allows for a string input. And these string inputs are mapped to the PyTorch version of it. So basically, for example, if we have a function like the get activation, it maps the choice, the string, to the correct syntax. Here I have two additional activation that briefly leaky relu has a small improvement over the standard relu. If you remember, relu outputs are 0 for any negative input. This can lead to the dying neuron phenomena, but leaky relu allows for a tiny non-zero gradient for negative inputs. In other words, it leaks a little and helps the neuron alive. The next one, Gelu, is basically a Gaussian error linear unit. It's a smoother, more modern alternative to RLU, and it has been recently used in advanced architectures like GPT. Okay, like I said, I want to make the design flexible. The reason is we want to do ablation experiment, but also learn something along the way. So let's introduce this themes list, which is basically the components that we are going to use in each of these hidden layers. So if you notice, we have layers, norms, and drops, and each one of them is a module, an N module list. And notice that I didn't use plain Python list, and the reason is this an N module list is basically talks to PyTorch directly. If we use a Python list, it will be invisible to PyTorch. You can think of it like the Python list, like a scratch piece of paper that you write the player name, but an N module list is like an official team roster for all of these layers, not players. So PyTorch, as the team manager, uses this roster to correctly find all of these parameters for the optimizer and also move them to the correct device and switch the modes for the layers, like, for example, dropout or batch norm during training or eval. So basically, this gives us a bunch of tools that we can use when we are building the forward method. Let's build the hidden layers. So for I in range of this number of hidden layers, we first append for each index corresponds to the hidden layer. We append the layer normalization and drops. And then we have a special final layer that is not following the same logic. So we have to write it separately. And this basically framework allows us to do that. Maybe you ask yourself why I didn't use sequential like before. Because our forward pass, as you will see, is a custom pass. And we are going to apply the layers from three different lists of layers, norms, and drops in a specific order. And then sequential is too simple and has a fixed data flow. However, this method gives us the flexibility that we need to build these custom pipelines. And also it allows us to deal with the special cases like the output layer. So the output layer doesn't need normalization and also dropouts, because normalization will distort the output scale. Remember that the output is raw logits that goes to the cross entropy, and the dropout will randomly suppress some of the prediction, which we don't want. Here we initialize the weights following the choice of the initialization method. And here we can write two functions to map to the choice of initialization method to the correct syntax in PyTorch, and also similar thing for the normalization. Here, if the choice is basically this, for example, batch or layer normalization, we map them correctly. So let's write these two functions. Okay, now we can write the forward method. First flatten, of course, and then knitting the toolbox together to make the pipeline, and return the final layer. Okay, so we are going to use some functions from before, like the train one, epoch, and evaluate. We already wrote this. We are going to just copy and paste. And then we can write the experiments. So we have different configs here. And for example, the control configuration is where we have the default initialization method, no normalization and no dropout. The second will be just adding one type of initialization, here the he timing initialization, and then next we add a batch norm over the previous one. So each time we change one setting. Next we do layer norm, and lastly we add the dropout. Okay, so let's keep a tab on the histories, adding the criterion, and then for each one of these configuration, setting up the model and the optimizer, and zeroing the history, and then we are writing the training loop. Okay, so populating the history, and then print out some of the result every few epochs. Okay, so with that, we're good to go. We can do the training. While this is running, let's just do a fast review of what we did. We basically start with this baseline and we add components one at a time. We measure the changes in the performance, and at the end, we will choose the best configuration. So while this is training, let's write a code that saves the best model, and then we can load it. So first saving, come up with a save path, and then save the best model. Then, of course, we can load the model and check if that's the correct model. So I'm going to just write this with some verification checks. And then after that, we can look at the visualize some of these tools that we had into using some of these tools that we have in utils, including the weight visualization, like weight distribution, and initial layer weights that is learned, basically the filters, and see if they are telling us anything. So here is the result. We see that he plus batch norm is overall the best model, and here is the result of the visualization. And if you notice, what we see here is really random static. And the reason is MLP flattened the image into a 1D vector and basically destroys all spatial information. Doesn't really know which pixels are next to each other. And this is a clue for us that MLP is not naturally suited for images. We can look at the weight distribution. I mean, they look fine, really, well behaved. So what we did with the initialization and normalization is okay and it's working, but they really don't tell us anything about what they represent. So this gives us this paradox about MLP. Why it performs well, while it really doesn't seem to be learning anything. It treats the image as a shuffled list of stock prices. This basically is a hint for us that it's really not generalizable. If we, for example, have an image of a shirt that is moved in the it's not centered like what we had in the fashion MNIST, the entire framework will collapse in the sense that it cannot basically predict that it's the same shirt. So we need something else, and we can include some of the assumptions that we have as inductive bias in this new architecture. So for example, there is an assumption of locality, the patterns that we found in an image. For example, the heel of a boot can be found in small local regions of the image. A very important assumption that the patterns is the same whether it's in the top left or bottom right of the image. We call this a translation invariance. MLP doesn't have either of them. It basically connects every input pixel to every neuron, and this way ignores locality. We will discuss a new architecture that we are designing from ground up with these two biases. And this way it allows the architecture to learn meaningful spatial features that look less like noise, like what we saw here. And it can generalize and can be used even with less learn parameters.